Yeah, that's good. And then
Okay,
home.
let's see. So Babette asked, do I see the chat window? Yes, I can see the chat. Wait. All right, I think I can begin. So hello to everyone there. This is Jonathan Feng, and I will be talking about standard WIPs. So before we start, let me say, actually I have two things I wanted to say. One is simply a congratulations to the organizers. This is something that usually is probably done at the end of the school, but given the circumstances, I think it's so extraordinary that I wanted to say it at the beginning of the school. I don't know how many of you students know, but this was organized starting 3 years ago. And I went back and looked at my emails and saw the first email from Marco, which was in September of 2018. And just to emphasize how long ago that really was, in my reply saying, yes, of course, I'd be happy to talk, I say, I've never had to enter a speaking engagement into my calendar 3 years in advance. It's a record. I'm expecting that just a few months before the school, the LHC will have turned on again, phaser will have found dark photons, and the lectures will be really interesting. And so that, of course, hasn't happened. The lectures we hope will be interesting, but the other two haven't happened, and a whole bunch of other things have happened. I wish I could go back and tell my 2018 self the things that were going to come up before this school took place. So it's really amazing. I see you all with your masks and the tape on the chairs and things. It's really amazing that this school is happening at all, and organizers deserve a lot of congratulations and thanks. I am sorry I'm not going to be there with you. I don't know if you know, but someone very important in my life passed away during COVID, and I have been going to the memorial service. And so unfortunately that prevented me from going, but I hope we'll be able to interact quite a bit despite that. Second thing is I wanted to just to note, as you most certainly have all heard, Steven Weinberg passed away just a few days ago. And this is obviously someone who is very important in our field, was very important in our field, and has impacted all of our lives through his work.
So we don't see our slides. Were we supposed to see our slides?
Oh, yes. Sorry, what happened? Okay. Okay, so sorry. So we started here. And then I showed some emails here. And then now we're here. Okay, so yeah, so Steven Weinberg is of course very important. I just mentioned one impact he had on my life. When I was a college student, one day I heard that the great Steven Weinberg was going to come and give some lectures. And so I wandered into the auditorium with about 400 other people and listened to, I think it was 4 lectures given over the course of a week or two. And those lectures turned out to be the Loeb lectures, in which he more or less predicted the size of the cosmological constant based on anthropic principles, which, as you know, is the only correct prediction of the cosmological constant ever. And so those were extraordinary lectures and quite inspiring to me as someone. This is basically the first physics talks I ever heard, first talks where a physicist was speaking to physicists. And I remember that with a great deal of fondness. Something that he wrote an incredible amount of things, of course, not just in physics, but something that he wrote, which I thought was interesting and appropriate for today, is a very short column published in Nature, where he lists 4 golden lessons for junior colleagues. So advice. First one was, no one knows everything. You don't have to. You don't have to know everything to get started in research. You should just plunge in and find out the things you need to know as you go along. Second, head for the messes. So don't just work in fields that are well understood. Actually, purposely don't work in the fields where there's a lot of open and confusing questions. Third, forgive yourself for wasting time. He's not talking here about truly wasting time like some of us do, but wasting time working on the wrong questions. He says that's inevitable. If you're going to work on something interesting, you're going to find that you're also working on things that turn out to be completely irrelevant and wrong-headed, but that's okay. And last, learn some of the history of your field, which I think is greatly underestimated these days. So we should all try to abide by these words of advice. I think they're very good. And I think that to some extent, these lectures will try to embody this sort of wisdom. Okay, so let me go ahead. So with the lecture proper. So this is the plan for my 2 lectures, and then there's a discussion that follows them. In lecture 1, I will begin with why WIMPs. Why should we even have an entire lecture series here dedicated to one kind of dark matter particle? And I will go through a number of motivations here. Then I will talk about one particular example, WIMPs and supersymmetry, which is not just any example, a very prominent one, but gives you a flavor for some of the things that have been just sort of the concepts and the major ideas in this field. And you'll see, in some sense, even more reason for why WIMPs are a very common topic in our field. And then somewhere around here, there will be a break, and then we'll go into lecture 2. I'll talk about WIMP detection, basically the direct detection, indirect detection, and collider searches for WIMPs, touching only very, very briefly on also sort of the possibility of seeing them through their virtual effects. And then last, I'll talk about WIMP variations. The WIMP paradigm has sprouted a number of extremely interesting sort of variations, which preserve the main virtues of WIMPs, but can give completely different implications for experiments, for astrophysical observables. And I don't want to leave you with the idea that this is like a completely done field, which you might think, given these first 3 sections, following Weinberg's advice, let's head for the messes, let's head for the places where there's a lot of new things that can happen. And so I'll give you some examples of modifications of the standard WIMP story that lead to extremely interesting, and I would say still not completely well-researched new ideas. Okay, so lecture 1. So let me just say, as with Anne's lectures, I do encourage a lot of interaction. I will try to stop periodically, but clearly just stop me and interrupt with questions if you have anything that comes to mind. I've actually purposely planned far fewer slides than I normally would for a lecture. And so there should be time to encourage, to entertain all those questions. And I think the organizers can help in just making sure to stop me if I go rambling on. All right, so let me start with why WIMPs. So let me start with this figure, which I prepared a number of years ago for the Cosmic Visions report. This is a large group report centered in the US, sort of taking stock of the field of dark matter, in particular particle dark matter, 4 years ago. And here you see what we've done here is basically placed a whole bunch of candidates, anomalies, and detection methods on a one-dimensional plot where that dimension is the mass of the dark matter candidate. And so just to be, to emphasize, every one of these ticks here is 1 order of magnitude, and every tick down here is 3 orders of magnitude. As you've seen, what I've done is actually condensed the lower side because there's just not enough room for all the ticks. And so up here we have, maybe let's start up here, the GeV scale. This goes the TeV scale, and you have here WIMPs. But then as you go down here, the lighter scale, you have sterile neutrinos, and then even lower, sort of the classic QCD axion. And these are, 3 of the standard golden oldies dark matter candidates, which have been discussed and talked about for many decades. What has happened since then is that these have been generalized and new ideas have come up. So, QCD axions are sort of now an example of ultralight dark matter, which is here. WIMPs have been generalized to hidden thermal relics, WIMPless dark matter, and we've also got black holes, which have sort of come to the fore more recently, asymmetric dark matter, and Simpson elders. All of these, of course, you will hear about, some here, but others in other lectures in these in the school. So there's a huge number of possible candidates. And then there are a variety of very interesting anomalies, things that don't quite match, which sort of indicate various interesting scales, some cases very specifically, in some cases more generally, but have some added interest to these regions of parameter space. And then we have all the different ways you can look for particle dark matter, direct and indirect detection at accelerators and colliders, as I've already mentioned. But then, there's a huge number of new ideas, nuclear and atomic physics, coherent field searches down here, microlensing up here for, more than solar mass black holes, and many others. And so you see here that, dark matter is an extremely broad field encompassing whatever this is. This is zepto EV. So this is 10 to the minus 21 EV, I think. And all the way up to PeV and sort of particle scales, and then even larger sort of solar mass scales here. And so these lectures are going to be confined to this region. So we're going to talk about WIMPs here, which I would define as particles with masses between about 10 GeV and 10 TeV, and which interact with the SU2 weak interactions of the standard model. Why would anyone want to focus on this tiny little region, given that there's so much more to talk about in a pair of lectures? The answer is that WIMPs have basically been the dominant, or certainly one of the dominant particle dark matter candidates for decades. It would be inconceivable to lecture about dark matter production without talking about WIMP freeze out. It would be inconceivable to talk about direct detection of dark matter generally without talking about WIMP direct detection. And similarly for indirect detection, without talking about WIMP indirect detection, that would just be impossible to imagine you would do that. And similarly, it would be inconceivable to talk about dark matter accelerators without talking about WIMPs at colliders. And so I am quite confident that the people listed here will not do the inconceivable, that they will actually talk about WIMPs in their talks. And so there will be a lot of overlap with other lectures. But the goal here is to do the following. First, explain why WIMPs in perhaps a bit more detail than they will have time to do. Why have they been a dominant paradigm for so long? Basically, what is their motivation? Second, I want to gather together some of their basic features before you hear about each of them in great gory detail. I know you've already heard from Josh, but in these following lectures. Third, I want to highlight the example of WIMPs and supersymmetry, which is sort of the example, the worked example in our field, which gives you both a feel for what can happen and in some cases, inspiration for what you hope will happen. The breadth of sort of the depth and breadth of the ideas that this spawns are just truly extraordinary. And last, to present some of the variations on the WIMP theme. Why? Because they have now, in many cases, sprouted their own independent literature, and they've kind of spread their tentacles throughout the entire literature, so that basically to really understand many dark matter papers, you should understand not just WIMPs, but their sort of what they led to. And as I say, they illustrate the richness of the circle of ideas. Now, these lectures are targeted to graduate students starting dark matter research. That was my instructions from the organizers, and I hope they will be useful for those of you in that category. I do, of course, understand that there are a broad range of people, both in terms of years of studying dark matter, in terms of your emphasis, in terms of astrophysics or particle physics, but I hope there will be something of interest to everybody in the room and online. Okay, so that sets out the goals. Are there any questions even before I get going with the actual topics? Okay, very good. All right, so let me start with the section on why WIMPs, basically the motivations. So this really goes back, again, many decades, in fact, almost a century, to the very, very beginnings of sort of particle physics, where roughly in the 1930s, people were observing nuclear beta decay. And to try to put this on a more quantitative foundation, Fermi introduced this whole idea of Fermi theory of nuclear beta decay, but including this thing called the Fermi constant, G sub f. And so in the simplest possible case, you can think of this as describing neutrons, which, as you know, is very important actually in cosmology. Neutrons do decay to protons after about 1,000 seconds, and that time gives you basically a value of the Fermi constant. So nowadays, the measured value of G Fermi is extremely precise, but roughly it's of 10 to the minus 5 inverse GeV squared. And then if you convert that to a mass scale, that tells you that there is a new scale in nature called the weak scale, which is m weak, which is about 100 GeV. We still don't understand the origin of this mass scale. After all these years, 90 years working on this, we still don't understand the origin of this mass scale. But every reasonable attempt so far introduces new particles at the weak scale. And so this is one of the essential pieces that motivates these WIMPs, because there are reasons we think there are new particles completely independent of the need for them in dark matter. Now, what does exactly this mean, understand the origin of this mass scale? That seems like a very vague sort of concept. I will, as we go along, give much better examples, but you'll see that we do have great hopes to really understand the origin of this mass scale in a way that's far more deep and insightful than our current understanding. One of the ways to put this on a more firm foundation is to ask the question of the naturalness.
Jonathan, we have a question.
Very good.
Hi, thanks. This might be kind of a basic question, but how did we go from the Fermi constant to that weak mass scale?
Okay. Very good. Thank you. And nice to see you, Catherine. The way we did it basically is just to say, look, this has dimensions of 1 over GeV squared. So let's just write that as 1 over some mass scale squared. And then what does that mass scale have to be to give me this Fermi constant, right? And so it's just a very, very, at this level, an extremely basic dimensional analysis sort of approach. Now, if you're asking in slightly more detail, you might say, well, why didn't you put in 300 GeV here? Because that'd be closer to the square root of this thing. And it is true, I cheated a bit. There's some little constants in here that are of order, 0.3 or something, and I stuck those in, and out this comes. But to be more honest, when I say the weak scale, I mean 100 GeV. If you want to call it a TeV, I'm fine with that. If you want to call it 10 GeV, I'm fine with that. Here, we're just really interested in a very broad brush, orders of magnitude. Okay. Okay, thank you for that question. Any others?
I think we're fine, thank you.
Okay, very good. So yes, please do ask as you see fit. Okay, so that was, so just to emphasize, this was sort of a very rough qualitative sort of way of thinking about the problem. There are slightly more quantitative ways to think about it, and they all come back down to understanding what's called the naturalness or fine-tuning or gauge hierarchy problem of the standard model. And this in turn comes back to the fact that in the standard model, we have something that's called the Higgs boson, which is a fundamental scale of particle. And so if anything, this gauge hierarchy problem became a lot more severe in the last few years, as we've actually found that there is such a particle in real life in nature. And it sure enough looks like a fundamental scalar. So now we even measured the mass very precisely. We have the Higgs boson mass of 125 GeV. Why is the scalar such a big deal? Why is the Higgs boson such a big deal, much more of a big deal than, say, the top quark, which was discovered in 1994? The reason is that Higgs bosons are scalars, and fundamental scalars are fundamentally different. If you ask what is the physical mass of a Higgs, well, of a scalar particle, okay, so this is a Higgs, so we have a propagator, and this little bump here is supposed to represent a mass, okay? This thing actually has several components. The first is a classical or tree level contribution, which is just simply from the fact that in your Lagrangian, you put in a Higgs mass squared. And that, of course, contributes to the mass of this actual physical particle. But there's more than that. We know, of course, in quantum field theory, we have a theory that's not just composed of tree interactions, but there's also loop level quantum corrections. And there are diagrams like this, where you can have a Higgs propagating through, but you have a loop of fermions, which could be any of the fermions that we know about. And you can calculate this. And for each one of them, you get a contribution that looks something like this. So, what is this? Again, this is sort of, I'm neglecting maybe a few factors, but, you have taken quantum field theory, you know the broad brush characteristics of these sort of diagrams. First, it's a fermion loop. So, those brings in a minus sign typically, well, always. Second, it's a loop. And so loop effects are always down by 1/16 pi squared. So I stick that in here. There are two couplings, lambda and lambda here, which are the Yukawa couplings of the Higgs boson to this fermion. And so I have a lambda squared, where that lambda is the appropriate Yukawa coupling for the fermion F. And then there's a scale to give the right dimensions, which has to be the mass squared. And so there's some lambda squared. And lambda here is basically the largest scale of the theory, the scale at which you believe your theory up to. And this is not normal. You do not see this if you write down a fermion propagator and write down a loop in there. And you can kind of very easily see why this is the case. You have the fourth momentum integral, but then in the denominator, you only have two momentum powers. One, because there's a propagator here, which is a fermion propagator, so it's 1/momentum. Another fermion momentum propagator, that's 2. So you have, p to the 4th over p squared. And so that's quadratically divergent, and it just takes whatever the top value of the integral will be. And so I think you have my notes that I wrote. This is done in a slightly more detail there. You can see equations there that are giving this, but this is essentially the root of the problem. If lambda is the Planck mass, which is sort of the ultimate scale at which we're very confident we don't have any idea what we're doing, that's 10 to the 19 GeV. And let's say the fermion is the top quark, which I pick because it has the largest Yukawa coupling. So that's a Yukawa coupling of order 1. Then you see that this is an entirely enormous number compared to the 125 GeV squared we have to get over here. This is, 10 to the 19 squared times 1 squared divided by about 100. That's enormous. And so get these two to cancel off to equal the 125 GeV squared, which we know from experiment, means that this and this have to cancel to 1 part in 10 to the 32. So you can always do that. You can always arrange for the classical value to be whatever is required to make this work. But it seems to be a rather remarkable fine tuning that's needed to just get something out for the 100 GeV squared. So that, in a nutshell, is the naturalist fine tuning or gauge hierarchy problem of the standard model. You can do various things. You can say, well, okay, sure, you put in lambda up to the 19 GeV. I don't believe the standard model up to the gut scale or the standard neutrino scale or something smaller. But even if you put in whatever you want, 10 to the 5 GeV here, that's still going to be a significant fine tuning. And if you go all the way down and say, well, I don't actually believe it beyond even a TeV. Okay, so I can just put in a TeV here. And if I put a TeV here, then I don't have any fine tuning to get 100 GeV squared. That's true, but remember what the lambda represents. It represents the highest mass scale at which you think you know what you're doing. In other words, that's the mass scale where new particles and new physical laws come into effect. So if you're assuming lambda is a TeV, well, you've already baked in the assumption that there are new particles at a TeV. And that's the whole point of this exercise. So the bottom line is that the resolution of this puzzle is, first of all, a central question in particle physics. And second of all, it most likely requires new particles at the weak scale, which you can see from different perspectives. And in particular, if you put in new particles here, you might put them in to cancel these large quadratic divergences. And that's the approach that's taken in many theories. Okay, so let me pause because I believe there's a question in the room.
Yeah, go ahead.
I would have a question regarding this hierarchy problem. The result for the self-energy you are presenting here, the lambda squared, the value, so the expression, this is only if you use cutoff regularization, correct?
Yes, that's right.
You would not
so this
have
is
such an expression. The capital lambda squared would have mass squared and mass, so the mass would be a new particle if it would be inside. Times a log of, I don't know, a new scale mu and so on. Standard model, you would not really have a hierarchy problem, right? The hierarchy problem would just appear if you introduce new particles, let's say particles from the grand uniparticular, I don't know, which are 10 to the 15 GeV and so on. And these will contribute, correct?
Yes, okay, very good. So in more detail, and this has of course been discussed at great length in the literature, all these caveats and more refined arguments are exactly what is required. So you're right, this assumes the very simplified standard mass cutoff approach. And if you want to say it in your way, yes, one could say what it really assumes in the background is that there is something beyond the standard model. But of course, well, there are reasons to believe there is something beyond the standard model. And I would probably quote dark matter, given the context of this talk, as a very important reason. But yes, so there are some interesting additional things to say about this. Well, I can maybe add something to the notes to refer people to further discussion if they like. But thank you for bringing up those points.
Anything else? No, okay. All right, I think we're good.
Okay, let's go on then. So the bottom line of this is that there are reasons to think that there are new particles, even if you just simply look at microphysics as you look for, subnuclear physics. But then, of course, there are other reasons from the opposite end of the spectrum, which is from cosmology and astrophysics, and that's related to dark matter. So in this school, of course, you'll be hearing about this in great detail, but let me just say some of the obvious things first. There are reasons to think that there is dark matter. And because we have some reasons to think it, we of course automatically have some criteria for the dark matter particles. First is that they should be gravitationally interacting, because that's what they do. That's how we see them in a number of ways. That is not a very useful criterion though, because everything gravitationally interacts, even massless particles like the photon. We know that photons are curved by gravity thanks to GR. So everything gravitationally interacts, and this does nothing at all in terms of helping us identify the dark matter particle. However, we also know that it should not be short-lived. These things should live for the age of the universe, or at least be present now after 14 billion years. And so that eliminates everything that decays on a short time scale, which includes, all the things I just X'd out. So all these quarks and heavier leptons and the Z, W particles, they're all eliminated, Higgs boson also. Second of all, this dark matter, as you've heard, I hope in the earlier lectures, is not hot. At least the dominant component should not be hot. And so if you go back and forth here, what that does is it kills off particles that are extremely light and fast moving that don't make good potential wells. So that kills off neutrinos and photons. And the last thing is that it should not be baryonic because of, for example, the BBN constraints you heard about. And so that kills off, things like atoms, when you might think, we could just have it made up of up and down quarks. So at least without turning on your head, basically you see that none of the known particles can be the cold dark matter. And so we need to find new particles. And this is, of course, extremely interesting, given that we were finding in particle physics reasons to have new particles as well. What do we know about dark matter? Well, as I just mentioned, we know very little. As you go back here, you see that most of what we know is not something. So not short-lived, not hot, not baryonic. And so we know a lot more about what it isn't than what it is. One of the few things, probably the only thing we know precisely about dark matter, is its relic density. So we know how much there is. Okay, so this is from LaPlante collaboration. Omega dark matter, H squared is 0.12 with this incredibly small 1% error bar. And you see it in these figures for the probability distributions for the baryonic dark matter and the cold dark matter. And you see they're very tightly constrained now. So this is something we do know about dark matter. And so the obvious thing to do is try to capitalize on this fact as much as possible. So what can we learn from this about dark matter's particle properties? Well, generically, you learn nothing. Okay, just because you know how much of something there is doesn't tell you anything about what it actually is. And so that is the case also in dark matter. But if the dark matter now is a surviving relic of the hot Big Bang, then we actually can learn a lot. If we believe that basically there's a production mechanism, which is thermal freeze out, knowing how much there is now actually tells you about the particle properties. Knowing the macroscopic quality of this particle tells you about the microscopic qualities of this particle. And that's an extremely interesting fact. So let's just turn to this. And I know that Josh's lectures will discuss dark matter production in great detail. Here, we're just going to sort of skim off the applications of pit whips. So thermal freeze out, what is this? So you assume, okay, so I'll refer to this figure. This is on the bottom axis temperature. So I don't know if you could see, but this is 10 GeV, 1 GeV. And so it's actually going down as I go to the right. But we do that because at the top scale is the time, which is going forward as we go to the right, which is sort of the way we'd probably want to think about the arrow of time. Then on this axis is y, the basically co-moving number density. You can think of this as sort of the number of dark matter particles. And we're plotting this for a dark matter particle mass of 100 GeV. And what's shown here is the basically number of dark matter particles as I go forward in time from the hot Big Bang down, 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 down. And you should follow like this solid contour for the actual evolution of the number of particles for a given example. So what happens is that at the beginning, there is assumed to be the hot Big Bang. We assume that it's very hot, goes to temperatures above, well, here it's 30 GeV, okay? So we assume that after inflation, maybe there's reheating, and then reheating brings us back up to a temperature that's above some tens of GeV in this case. And in that case, there's we have a dark matter particle X, which is inertially in thermal equilibrium because it's very hot. And so everything is pretty much in thermal equilibrium. And what that means is you have a thermal equilibrium number density, just formula you can get from your statistical physics course. In terms of the actual reactions at the particle level, this means that XX particle annihilation into fermion bar is a very efficient process, and also the reverse. So fermion bar, we can think of this as E plus E minus or QQ bar, going the other direction is also very efficient. And that fact that that arrow goes both ways is basically the statement of thermal equilibrium. So we have some thermal equilibrium in the very hot early universe. But then the universe cools. Okay, so it starts dropping in temperature. And what happens then is that we start losing the ability to go the other direction. So these dark matter particles, like I have here 100 GeV, they can continue to annihilate with each other into, say, E plus E minus. But once you make these E plus E minus, they kind of thermalize and come to typical temperatures of order that are energies of order the temperature, say, 1 GeV. And if you have a 1 GeV electron and a 1 GeV positron, obviously you can't make 100 GeV particles. So you can't go the other direction. And so you drop out of thermal equilibrium. Well, you are in thermal equilibrium, but you don't have the initial thermal equilibrium number density. You start going down and down. And in statistical physics, we know what this is. This is the Boltzmann suppression. This E to the minus M over T. So you start losing heavy particles, heavy compared to the temperature. Okay, if this was all that was going on, if the universe was a closed box which is cooled, then you know what would happen. This is just normal statistical physics. You would just have fewer and fewer X particles, and they would drop exponentially, which is what's shown by this dashed line here, and you would eventually have none left over. But the universe is a very interesting place. Not only does it cool, it also expands. And so what happens is that instead of dropping to 0, you actually get off of this curve and you approach some asymptotic value. And this is because these X particles eventually become so dilute that they can't even find each other. So at this stage, the X particles can't annihilate to FF bar, even though energetically they're allowed to. And again, FF bar can't go back to XX. And so these just decouple in terms of this process. And this is what's called thermal freeze out. And so you get off of this and you're left with whatever number density of dark matter particles you're left with, okay? And so over here on this axis is shown omega X, dark matter omega. And from what I said previously, this is the target. You want to hit this. This would be all the dark matter, not too much, not too little. Now, clearly, what happens is that where you get off this extremely steeply falling curve has a lot to do, determines where you end up. And so where do you get off this curve? Well, it is determined by the interaction strength. How strongly do these particles annihilate? And here I've shown various color bands. And basically what's changing in the colored bands is the annihilation strength or the annihilation cross-section. And so if you annihilate more strongly, you stay on this curve longer, and then you end up with fewer particles and fewer particles and fewer particles. On the other side, if you annihilate more weakly, you get off earlier and you have more and more. And each band here is basically an order of magnitude in cross-section. Okay. Now, if you look carefully, it's also about an order of magnitude in terms of omega X. Okay, this is 10 times too much dark matter, 100 times too much, 1,000 times too much. And so it looks like it's just inversely proportional to the annihilation cross-section. And in fact, that's exactly true. So we'll see that in a little bit, but let me first just talk about where you get off. So in more detail, the Boltzmann equation is determining this entire evolution. So this is dN dt. N is the number density of dark matter particles as a function of time. This number density has 3 contributions to it. The first is dilution from expansion. So this is just the Hubble parameter, is A dot over A. And so if we just had this this would be basically n dot over n is minus 3a dot over a, which is just telling you that n scales as 1 over a cubed, which is just that the number density scales as the inverse of the volume, which is what you would have if you had no number changing interactions. However, there are number changing interactions. And so you have chi annihilates to ff bar, and that gives you a decrease in dn dt. I mean, dn dt is negative, and so that's this term. And then there's also the time reverse process, ff bar, which goes to dark matter, which gives you this term. Okay, and this is the number, thermal equilibrium number density, turns out. Okay, so this is the particle source term. This is the particle sink term. And this is that dilution from expansion term. Okay, so we would then just solve this numerically, but we're not going to do that here, of course. What we're going to do here is just understand the broad features of it. And the broad features are that when n, when this is a very important term, you stay in thermal equilibrium. But this eventually stops being important. Eventually, this interaction rate drops below the expansion rate. And that's when you freeze out. And that's effectively the statement that it becomes too dilute to annihilate. And so this is the interaction rate. Okay, this is the expansion rate. And you have just to simply ask, when does this happen? And so you can go back to your thermal physics textbooks and find the number in thermal equilibrium for a non-relativistic particle species. It looks something like this. Okay, has dimensions of mass cubed, 1 over length cubed, mt to the 3 halves. Then there's this Boltzmann suppression factor, e to the minus m over t. So that's this term. The cross section for annihilation, we'll talk about this in gory detail later, but it's just 1 over the mass scale squared by dimensional arguments. And then typically there's some coupling alpha squared in there. And then this thing is just the Hubble expansion rate, and this goes as t squared over m Planck. So basically, when this is true, when the temperature makes this true, that's when you get off this curve here. Now, if you didn't know much, you would say, look, I know about thermal physics. I know that there's something called Boltzmann suppression. And so as soon as this temperature drops below the particle mass, instantly the particle number is going to drop to 0. Instantly, my interaction rate is going to drop out, and I will just get off at that point. But that's not actually true. And the reason is that this expansion rate is suppressed by m Planck, which is a reflection of the fact that the expansion it has to do with gravity, and gravity is weak. And so not every mass parameter in this problem is of order the same thing. There's this huge giant 10 to the 19 GeV down here, which is saying that the universe expands slowly, and we have to take that into account. So basically, what you can do is you can group all these mass terms in this alpha and put them all over here. And what you're going to find is that this e to the minus m over t has to be equal to mass over the Planck scale. Okay. In other words, if I take the log of both sides, m over t is about given by this. And then if you plug in the mass scales here of a weak scale, you find that m over t is not of order 1, it's actually of order 25. Okay. And so this is very interesting though. This is extremely interesting given such a rough analysis. What it says is you do not freeze out at, in this case, 100 GeV. Actually, you freeze out at temperatures that are quite a bit less by a factor of 20 or 25. And you see that here. The place where you get off this curve is here around 4, 3, 5 GeV, something like this. And that's much less than the actual mass of the particle. Okay. Now, it turns out that the relationship between where you get off and the annihilation strength is wonderfully simple, as I already mentioned. We saw it just eyeballing it, that there's order of magnitude change in cross-section, and that leads to an order of magnitude change in omega x. Turns out this is very approximately true. And so we have this relationship. And the cross section, as I mentioned before, it's got to have units of 1 over mass squared. So this is a mass squared, and it typically has 4 couplings. If you have a diagram like this, so XX annihilates the QQ bar, you're going to have a coupling here, and of course that's the amplitude in the cross section. It's squared, so you get 4 powers of coupling. So basically, you can write this equation, where the only thing I've assumed here is that all of the mass scales in this annihilation process have ordered the same thing, namely the mass of the X particle. And so I don't have like a super heavy mediator particle in the T channel here, say. But with that assumption, we can now ask what masses and what couplings determine the correct omega X. So keeping track of all the constants that are hidden in this proportionality sign here, we find that if you put in 100 GeV for the mass scale here, the weak scale, and the weak coupling 0.65 here, okay, and ask what omega X comes out, the answer is omega X of about 0.1, which is of course exactly within the limits of our rough calculation here, is exactly what you want for the right amount of dark matter. In other words, what I'm saying is that as you come down here, you want to be on this curve because that gave you, 24% of the universe in dark matter. But that curve is exactly corresponding to a cross section that you'd expect for a weak mass particle, 100 GeV particle with weak interaction couplings, Gx of 0.6. And so this is a remarkable coincidence. Okay, first, just stepping back, this is remarkable because we're saying that the macroscopic astrophysical properties of dark matter, namely how much there is, are linked to the microphysical particle physics properties of dark matter, namely what are its properties, particle properties. So that's an amazing fact, first of all. But second of all, it's telling us that all those motivations we had for weak scale matter give you motivations for particles that naturally have the right thermal reluctancy. And that's what's called the miracle. So there's a number of ways to say this. And when I introduced this term years ago, what I told people is that the WIMP miracle is telling you that if someone gave you $10 billion, and so it said, go build a particle physics experiment to find dark matter, what you would do is you would build the LHC or the SSC, but a big particle collider, because that would be exactly the thing you want to make dark matter, to find dark matter. So it's just an incredible coincidence that for other reasons, we've had reasons to build the Large Hadron Collider. And it's very promising that there's this connection. Okay, I see hands in the audience, so let me take questions.
Hi, thanks. So do people always assume instantaneous decoupling between the standard matter particles and dark matter particles? And if not, does the WIMP miracle still work if you don't have instantaneous decoupling?
Okay, thanks. So no, we don't really assume instantaneous decoupling. What we do is actually, do this correctly, right? So the Boltzmann equation is a continuous equation, and if you know dNdt, you can just step forward in small time increments and do this, basically this differential equation solution numerically, right? So it's a gradual decoupling. And in fact, exactly where you say the particle has decoupled is open to some, if you want to get into the nitty gritty, it depends on your definition. This is one definition, but people sometimes put other little constants in here. But anyway, the point is that, this is a gradual decoupling from this steeply falling curve. Of course, because it's e to the minus mt, in some sense, it's very specific. It happens, it definitely hasn't happened at 7 GeV, and it definitely has happened by 2 GeV, right? So it's got a very narrow window when it all happens. But we do it very continuously in terms of the amount of time it takes. It's a significant fraction of the age of the universe at the time that it's happening, right? Does that answer the question?
It does, thank you.
Okay. Okay, and there's a question in the chat. Aren't we assuming that the freeze out is happening in the non-relativistic regime? So the answer there is yes. So you can see that here, when I put this formula in, this is actually only valid for non-relativistic species, right? You know that if it's relativistic, it's actually the number density goes as T cubed. So in some sense, yeah, what I've really done to be more precise is to put in the assumption of a non-relativistic freeze out. And then as I go through the calculation, I find that in fact, the answer is that it's pretty non-relativistic. And so that sort of at the back end, in turn, sort of consistently, self-consistently justifies my assumption at the beginning. But yes, this is assuming there's what we call a cold relic. And I'll talk a little bit more about that in the next slide. Yeah, and that's the, let's see, the Maxwell-Boltzmann distribution essentially. Yes, I think that's what I've basically said here. This is the assumption we're making. Okay, any more through the chat? No more through the room? Okay, let's go on. Okay, oh, one more, go ahead.
Yeah, go ahead.
Okay, I was just wondering if you know how other dark matter theories explain this like miracle, if it matters to them, if the mass is not exactly on this scale. Would you happen to know that?
Yeah, okay, good question. So what about other dark matter particles? How do they get this scale? Basically, in most, I might even say virtually all other frameworks, the mass scale or the relative density is just put in by hand. So for example, if you have axions, through a detailed calculation, you can find that in terms of parameters of the theory, namely the mass of the axion and the axion decay constant, you can find the relative density of axions. And then you simply say, well, if I want that relative density to be the correct one, then that tells me that my QCD axion better have a mass of 1 micro EV. A priori, there's no reason to think that that thing should have been a micro EV rather than a milli EV or a pico EV, right? So it just tells you that. It's the same thing here, that the relative density tells you, in some sense, what the couplings and properties of the particle are. But the miracle part is simply the fact that we end up with a preference for parameters that are exactly the parameters that we would have got from the gauge hierarchy problem. So it's the coincidence of two a priori completely different motivations that gives you, something interesting. But yeah, in other dark matter candidates, you can get the right relative density. You just have to tune the parameters for reasons that have no motivation other than the fact that you want to get the right relative density. And so I'm sure you'll talk about that in the other lecture with other ways of getting the right dark matter relative density from instead of freeze out, but freeze in, or various other methods. But this property of WIMPs, this WIMP miracle, is really unique, and is a large part of the answer of why WIMPs, why people talked about WIMPs for so long. Okay, I see no other questions. Are there any? If there are, just jump in. I really appreciate these questions. They're excellent questions. And yeah, okay. All right, so let's just talk about this a little bit more. So as I said, we can do this numerically. With this extremely simple analysis, we got M over T was about 25. If you do it numerically, that's pretty much spot on. Maybe it's more like 20, but it's in that range. Okay, so let's just sit back and understand some of the implications of this fact. So again, since this is going to work out to be non-relativistic, let's set the kinetic energy is 3 halves kT, as you know from your basic thermal physics course. That means the temperature is 1/3 mv squared, where I'm putting in the non-relativistic kinetic energy formula here of 1/2 mv squared. Okay, we're being extremely simplistic here. But this then already tells us that if I know m/t is 20, then this is 1/20th m, and I can now solve for v. And so v is about 1/3 at freeze out, okay? So at freeze out, dark matter was, I would say, neither ultra-relativistic. This velocity is not of order 1. This is 1/3 of the speed of light. At the same time, it's not totally non-relativistic either. It's not, velocities of several orders of magnitude below the speed of light. So this is a very interesting fact you want to keep in mind, and it'll come up in this lecture series a few times, and it comes up as you do dark matter research, especially WIMP research, all the time. This 1/3. One thing that's important about this is that 1/3 is not the velocity of dark matter now. You know that the dark matter in our neighborhood now can be determined by the virial theorem, where you basically set the potential, gravitational potential energy around us equal to the kinetic energy around us. And if you do that, you know that the dark matter velocity is 10⁻³ around us for an incredibly large variety of dark matter candidates. It doesn't matter if it's 100 GeV or 1 eV. Basically, all dark matter now has a velocity of 10⁻³. And so that's a huge difference. Okay, freeze out is at 1/3. Now it's 10⁻³. And this is a very important difference to keep in mind. And if you were born 10 or 20 years ago, you could have written about 15 great papers just based on this simple observation. What this means then also is that if you have a 100 GeV particle, the freeze out is at temperatures about 5 GeV, which is times of a nanosecond after the Big Bang. This is not at the mass 100 GeV. The temperature is not 100 GeV, and the time is not a picosecond. And so you see this mistake in all sorts of write-ups, people talking about it. If you could really understand freeze out, you would probe the universe back to times of a picosecond. That's not true, and it's off by about 3 orders of magnitude. And it's simply because of this fact that the freeze out is not at 100 GeV, it's at 5 GeV. It's always a little bit less. Another important thing to keep in mind is that this whole process I've talked about, which I call thermal freeze out, is maybe more specifically called chemical freeze out. That is, it's when the number changing processes freeze out. And it does not mean that the dark matter is completely decoupled from the standard model, because there is still the possibility of energy exchanging interactions, say dark matter fermion from the standard model, basically elastic scattering, as they've written it here, right? So energy exchange still happens, and typically does, long after the chemical freeze out happens. When this stops happening, we call that kinetic freeze out, but that's typically much later in the universe's history. And that is important if you want to understand things like structure formation and other more sort of astrophysical topics. Okay, now one last note. The WIMP miracle is not a precise coincidence. Okay, so I've maybe painted it as a little too precise. You can easily, within a WIMP model, find that it's off by, say, an order of magnitude, or maybe even 2 orders of magnitude. And so, there's a lot more to say about this. But at this stage, the point simply is that it's tantalizing that it's not off by, 15 orders of magnitude, okay? A priori, we're connecting completely different ways of looking for new physics. And it could certainly be off by 15 orders of magnitude, but it's not. And the fact that it's close is actually our strongest quantitative hint that our attempts to understand the universe on the largest and smallest scales may actually be related. What right do we have, say, turning on the LHC to think that we're going to learn anything about dark matter? At first sight, none. But here's a quantitative hint that maybe you're actually looking in the right place to find dark matter. Okay, that concludes the discussion of WIMP miracle. But there's a lot more to it than that. The WIMP miracle is, I guess, by now very well appreciated. But its success relies on another less well advertised miracle which in some sense was sort of hardwired into the analysis so far that probably you didn't even explicitly think of this as the assumption. But that assumption is that the dark matter must be stable. Okay. Why do we think that dark matter should be stable? We're talking about a new 100 GeV particle. What right do we have to think that it should be stable? A priori, we don't have any right at all. It's incredibly unnatural. You have an extremely heavy particle, and we know that all particles above a GeV are unstable, everything we've ever seen. So here's the picture we want. We got a bunch of standard model particles lying down around here. Then there's a new particle, maybe a bunch of new particles. But we want them to have one stable particle, probably the lightest one. And so we wanted, if there's decays of these higher ones, to all stop here at this lightest new particle. But this lightest new particle is not light, it's 100 GeV. So what right do you have for it to stop here and not have more arrows that have it decay down to the standard model? Turns out there are actually sound experimental data reasons to think that that actually might be true. And so that's yet another remarkable fact. And this is what I call the discrete WIMP miracle. And so what does this stem from? So typically these new particles, we want them to be dark matter. We also want them to solve the gauge hierarchy problem. So what do they have to do? Well, the gauge hierarchy problem means that they have to introduce new quantum corrections like this to the Higgs boson mass to cancel those offending incredibly large ones from the standard model, okay? So typically, you don't have to, but typically when you make a scale, a theory of new weak scale physics, you have new particles that also couple to the Higgs like this, okay? However, we have done an incredible number of precision electroweak measurements looking for standard model interactions, which can be mediated by a new particle. So this, is basically what would be called an effective four-point interaction between standard model particles. And these are extremely highly constrained by many experiments, notably by LEP, the Large Electron-Positron Collider that ran at CERN from about 1990 to 2000, which did, as you probably know, made millions of Z's and did extremely precise electroweak measurements. And in doing so, basically eliminated the possibility that for various standard model assignments of these 4 legs, that there would be new particles in here at the 100 GeV scale or even the TeV scale mediating these interactions, okay? So what I'm saying here is that there are reasons for aesthetics, the gauge hierarchy problem, that we want these kind of diagrams, but very hard data reasons that we don't want these kind of diagrams. And yet, if you have a 100 GeV particle that does this, it generically does this. And so what do we do with this? Well, the simple solution is to notice the following simple fact that in this diagram, every single new particle interaction has 2 new particles at the vertex. Whereas in this diagram, they all have 1 new particle at the vertex. So if I impose a discrete parity so that all interactions require pairs of new particles, then I can keep all of these diagrams, which are the good ones, and eliminate all these diagrams, which are the bad ones. Okay, and this has been done in time after time again with new particle theories. And the basic bottom line is to eliminate these huge problems you get, usually you need to impose a discrete parity. Now, that's just the purely particle physics reasoning, but what does that mean for cosmology? What it means is that, going back to here, this is exactly the scenario that will happen when you impose this discrete parity, because you'll decay here. Once you get here, the only kinematically available decays are to 2 or more standard model particles, but we've eliminated all vertices which have only 1 new particle at the vertex. And so there's no way this last decay can happen. In other words, this discrete parity has preserved the stability of at least 1 new particle. And that's exactly what we hope will be dark matter. So this was, the example of this was R parity and supersymmetry, which Fayet and Farrar proposed long before, but then this was sort of laid out as a general principle in these nice papers by Cheng and Lo and Jose Woodka much later in 2003. But the bottom line is that there's another remarkable coincidence. Particle physics independently motivates particles that are stable enough to be dark matter at the 100 GeV weak scale. Okay? And that's an essential bit of this whole story, which is often overlooked, but is in some sense, it's a discrete wimpless miracle, which complements beautifully the continuous WIMP miracle, which is the standard WIMP miracle. Okay, so at this point, I've finished with what I wanted to say about the why WIMP section, the motivations.
Sorry,
for
Jonathan,
WIMPs.
we have a question.
Very good.
I'm not sure if I'm appreciating this parity symmetry here to forbid these interactions. I mean, why do we expect something like a Z2 symmetry, or maybe you'll get into that. I guess I'm not appreciating this discrete WIMP miracle.
Okay, well, hi, Max. The basic point is it can be very phenomenologically driven. You can just say, look, I want to make a theory which solves the gauge hierarchy problem, but I don't want it to violate all sorts of other constraints, right? Obviously, then it wouldn't be viable. And so I find that when I put this particle in and I don't put in some new symmetry or something, it gets me all these problems. And so I noticed that I can eliminate all of them with the symmetry, right? And of course, you could eliminate all these hand by hand or suppress each of these couplings hand by hand. But number one, that's very unsatisfying. Number two, they'll pop back up at higher orders and things. So the way to get rid of this entire class of problems is to use a symmetry. And the discrete symmetry is sufficient, basically a Z2 symmetry that is, like -1 for new particles, +1 for standard model particles. And you require that the product of all the +1s and -1s be +1 at the vertex. And so that will just eliminate, basically that will require an even number of new particles at every vertex, right? And so that kills off all these and keeps all these. And so it just beautifully does the trick. Now, if your question was, well, that seems very ad hoc and by hand, you're right, absolutely. So where did this discrete parity come from? Well, okay, then we have to work in specific contexts. So in supersymmetry, for example, R parity is the parity I'm talking about. And this has been discussed as maybe being a remnant of a larger symmetry, some continuous symmetry like a UN B minus L or something from a grand unified theory. And somehow things break down, and eventually you're left with a remnant, which is this discrete Z2 symmetry. So there are some contexts in which we can sort of embed that discrete symmetry in a larger, maybe more satisfying framework. But it varies from theory to theory. And to be truthful, a lot of them don't go that far. They're just simply imposed by hand. They're just symmetries that can say are empirically motivated.
Thank you, that answers my question.
Okay. Okay, great. Any others? Okay, so let's go on. So the next section is I'm going to start talking about WIMPs and supersymmetry. Okay. Before I do that, let me just say a few words about very specific BSM models. For the reasons mentioned above, WIMPs appear generically in many BSM theories. Okay, and there's a well-worn path to how this occurs. So you have some problem, like the gauge hierarchy problem, or some anomaly, like the G minus 2 of the muon, and you want to fix or resolve this. So you propose some new weak scale particles. They then help some things. They do what you want. They satisfy your initial motivation, but then they strain electroweak fits, like the ones I was talking about. They screw it up. They predict that there's a 4-point electron interaction that's way bigger than what's actually known. And so then you impose a discrete symmetry to improve these fits, and that makes your theory viable again. And then, even though at this point, all you've been talking about is particle physics, you realize that an ideal dark matter candidate emerges because number one particle is stable. Number two, it has the right relic density through the most generic possible production mechanism possible, namely thermal freeze out. And so then, you say, yay, we declare victory, and you promise that you will write 3 follow-up papers which explore the cosmological implications of your model. Now, this has been realized many times. So the granddaddy of them all is neutral needles and supersymmetry, first proposed by Chaim Goldberg in 1983 and Ellis et al. In 1983. And I will talk about that. There are then later realizations of this, for example, in extra dimensions, a Kaluza-Klein photon, or more precisely, a Kaluza-Klein hypercharged gauge boson in universal extra dimensions, which Geraldine Servan and Tim Tate and Xin-Chia Cheng, Konstantin Machev, and I pointed out also has this same sort of story. Cheng and Low, shortly after their previous paper explaining how this is such a generic way to do things, did work it out in the context of little Higgs theories, where there's this light T odd particle. T again is a discrete symmetry. And so, there are a number of possible examples one could give. So here I'm going to focus on supersymmetry as an interesting example because it's just got its fingers all over the place. But if you want to see other examples, please take a look at these. I think I've referenced them, or I will reference them in the notes. Okay, so now we're going to talk about supersymmetry. So supersymmetry, of course, is a huge paradigm, which itself was a dominant paradigm for decades. I find that nowadays, it's not like, you can't be a good graduate student if you don't know supersymmetry, which more or less was the case 2 or 3 decades ago. So let me start by just explaining what supersymmetry is and drawing out the key points for the dark matter implications. So supersymmetry predicts a particle that, partner particle, I should say, for every known particle. And these partner particles have to have opposite spin statistics. So for every fermion, you put in a boson. For every boson, you put in a fermion. And there's spin 0, spin 1/2 partners, and there's spin 1/2, spin 1 partners. And basically, for reasons I won't go into, all of the matter of the standard model is in this case. So the matter particles of the standard model, of course, are fermions, so they're this side, and we have to introduce new scalars. And this is the gauge part of the theory. And so the gauge boson is, of course, spin 1 in the standard model, and we have to introduce what are called gauginos, spin 1/2 fermions for each of those. Okay, and so here is the picture. So for new particles, we have to introduce spin 0 squarks, which are just the scalar partners of the spin 1/2 quarks. We need spin 0 sleptons, stands for scalar leptons. Then, as I mentioned, all the spin 1 particles in the standard model, of course, need to have spin 1/2 partners. So we have to have gauginos in general, but in specific, we call them the BINO for the hypercharged gaugino, WINOs, 3 of these for the SU2 gauginos, and 8 gluinos for the 8 gluons. Okay. Then, of course, we've actually also discovered this fundamental scalar of the Higgs boson. So actually, that's the one example where this is the spin 0 for the standard model, and spin 1/2 has to come from supersymmetry. So we have to get spin 1/2 Higgsino. So basically, it's a doubling of the standard model, okay? But, and so you see that here's existing particles, the standard model, and here's supersymmetric particles, which are a doubling. But if you look carefully, it's actually more than a doubling, okay? Because this is actually not the standard model. It's got all the quarks and leptons and our gauge bosons and the Higgs, but it's actually got 3 more particles over here, which are in the Higgs sector, scalar particles. So why in the world would you complicate things even further by throwing these things in first before you double the spectrum? The answer is that if you just simply have the standard model, so you have then just this Higgs boson and not these 3 things, supersymmetry tells you you've got to add a Higgsino. So you put in this Higgsino over here. Okay. But the problem is, this is now a new fermion, and fermions contribute to 3-point triangle anomalies. And this then, you know that the rest of this was all good. All these standard model fermions kept the anomalies to 0. This introduces new anomalies, and so it screws everything up. And now you have an anomalous theory, which is not a well-defined mathematical theory anymore. So you could either just drop supersymmetry completely at that point, or you can try to fix it. And the way it's fixed is that we include, kind of, you can think about it this way, we want to include another Higgsino that has sort of the opposite charges to the one we were stuck with, and that will cancel off the anomalies. And then if I work back, that means I have to have a new Higgs boson. And so then I have a 2 Higgs doublet model, which then I fully supersymmetrize, and it gives me all these particles. Okay, so that's the reasoning. But for dark matter, this is fairly important because actually these Higgsinos contribute to the dark matter component. So it's, I kind of stress this, it's not simply a doubling, it's a doubling plus some. In other words, we first extend the standard model to a standard model plus 2 Higgs doublet, and then we supersymmetrize. And what that means is that you have not just the known Higgs boson, but a typically heavier Higgs boson, plus a CP odd Higgs boson and charged Higgs bosons. And then all of their partners, Higgsinos and charged Higgsinos. Okay. Now, why would one want to go through such a gory extension of the standard model, doubling the degrees of freedom that we know about? The answer is going back to this gauge hierarchy problem. So if we have this Higgs boson mass, as we talked about before, it has a classical tree-level contribution. It has these quantum corrections from standard model particles, which were giving us large corrections. If we throw in all the new super particles that we just had on the last slide, they also contribute to the Higgs propagator, the Higgs mass. And so they contribute through diagrams like this. So we're adding, for every fermion, we're adding in a scalar. So I've got this dashed line here. There are 4-point renormalizable scalar interactions. And in supersymmetry, it turns out, because this is a lambda, supersymmetry demands that this coupling be lambda squared. That's in some sense the whole point of supersymmetry. And so this then has a very similar form to this one, with a lambda squared. Again, there's just one p squared from this one propagator, so this quadratically divergent, so another big lambda squared loop factor. But the critical thing is it's not a fermion, so there's no minus here. And so we have a plus here. And these two then cancel each other off at leading order. At non-leading order, which is good, right? So then now this enormous giant thing is canceled off by something else, and we don't have to fine tune these combination with the tree level thing to get the physical thing. At non-leading order, the quadratic divergence is canceled off, but there's sort of logarithmically divergent pieces, which go like this, and have the mass scale restored by this fermion mass, like this. And so this is the resulting quantum correction. But now this is actually in the form of something you could think of as a correction, because this log, even if this lambda is, Planck scale, this is still not a huge number. It's like about 30 or something. And then we have the loop factor, which knocks it down. And so basically, this whole thing here is typically smaller than this thing. And so the fine tuning or naturalness is, fine tuning is gone, naturalness is restored. So for lambda of M Planck and F, the top quark, this, if you require 1% fine tuning, namely that this thing is not more than 100 times greater than that, leads to the fact that this new particle you're inserted here, which comes with its mass here, has to be less than about a TeV. If you drop this down to M weak, then this could be 3 TeV. But the bottom line is you don't have giant quantum corrections, but the price you pay is you have a bunch of new particles, which can't be arbitrarily heavy, because if they were, they would reintroduce this problem, okay? So we have supersymmetry with a whole zoo of new superpartners, which more or less all have to have masses at the weak scale. Now, if you look at this carefully, you realize that that's not actually true, because I've taken as my example the top quark here. So this is the top squark, which has a lambda of 1. If you took the electron, so you have an electron here, and this electron here, it comes with a Yukawa coupling. That's the Yukawa coupling of the electron, which is a tiny number. And so then you could tolerate having much, much larger fermion masses if they're this electron and still get no fine tuning. And it turns out that is true. It turns out that this is not for the electron. This is not the leading piece. It's actually a 2-loop piece, which really gives the dominant piece. And so it turns out that this electron can't be enormously heavy. It could be like 10 TeV and still not give you more than 1% fine tuning. So I guess my point is that there was natural argument. There are various kinds of bounds from different superpartners. They're not all the same. They don't all have to be at the TeV scale. Some can be 10 TeV, but nevertheless, they can't be, 10 to the 16 GeV either. Okay, so that's the motivation for supersymmetry. Now, what about this whole story I told you about the stability and the discrete symmetry? Sure enough, it happens right off the bat. In fact, it happens in some sense even worse than you might imagine. Because in supersymmetry, as soon as you start putting these new particles into your theory, not only do you sort of get these very fine deviations in electrowave observables, you get this massive, huge violation of known fact, which is that the proton decays. And for all intents and purposes, it decays instantly. Okay, it doesn't live for the age of the universe, and certainly doesn't live for 10 to the 34 years, which is the current bound. So basically what happens is you put in these new superparticles. There's some squarks. So this is the strange squark, it's right-handed, doesn't matter. Basically that introduces proton decay because you can have an up and a down quark turn into this squark, which then turns into a positron and an up bar. And if I add on this up spectator quark, what I've really done is I've had a proton decay to a pion plus a positron. And as I say, the lifetime that you can calculate if this is at the weak scale is incredibly small. And so protons obviously don't do this. So what do? Well, we do exactly what I said. This relies on the fact that there's a vertex here with one super particle, one new particle. And so if we forbid this with R parity conservation, where R parity is defined in this particular way. Okay, so it's got some detailed form in terms of baryon number, lepton number, and spin. But the key point is that if you define it this way, standard model particles have R parity of 1. All the new SUSY particles have R parity of -1. And if you require that the product of all the R parities at the vertex is 1 in every single interaction, that eliminates all these effects, but does not eliminate this this cancellation. Okay, and so it's beautiful. You basically keep all the good stuff, get rid of all the bad stuff, and your theory is viable again. Incidentally, it also gets rid of a bunch of these troubling 4-point interactions I talked about previously. And so then the final particle, the final result is that the lightest SUSY particle is stable. It's called the LSP, and now it can be a potential dark matter candidate. Okay. Any questions? All right, so, oh, good question I see in the back there.
Yeah.
It's a basic question about supersymmetry. Supersymmetry relates bosons to fermions, but it doesn't state anything about the supercharge. So if I take a standard model boson, how can I know my superfermion will have spin 1/2? Why not 3/2?
Say it again at the very last part. Say it again. If I take a spin 0 particle, how do I know the partner has spin 1/2 and not what?
how do I know which will be the spin of the super partner?
Okay. So I think, tell me if I'm wrong, but I think what you're saying is, okay, I accept that supersymmetry has to give me something with the opposite spin statistics, but why can't I have like a spin 0 particle partnered with a spin 3/2 particle, or something like that? Was that the question?
Okay, that was my question.
Okay, very good. So good, yeah, that would partner a boson with a fermion. But it turns out that supersymmetry is a much more constrained and deep theory than that. Basically, what you have, let me put it this way. In the standard model, we have a symmetry, Lorentz symmetry, where if you have an electron, you can apply a boost operator to it and make it into an electron that's going somewhere. And so in some sense, the fact that we have Lorentz symmetry, we have boost operators, is saying that if you predict you have an electron at rest, you also have a particle in the theory, which is a particle moving. Okay, that's maybe a weird way to think about symmetries, but that's one way to think about them. In supersymmetry, you have also an operator, but it's a new operator. And it says that whenever you take a known particle, it also gives you a new particle. It turns out this operator is effectively a spin 1/2 operator. It changes the spin of the first particle by a half to the other one. And so you can apply that to every single particle, but you can't jump 3/2. And so it ties together things into spins that are different only by 1/2. In the n=1 supersymmetric particle case, there are more fancy supersymmetric theories that can sort of tie together particles that have larger spins. But here I'm talking about only n=1, so-called n=1 supersymmetry. And this one operator is basically moving up and down spins by 1/2, but not more than that. Does that help?
Oops. Yeah, go on.
So in these other supersymmetric models, could I have something where I switch it by 3/2? I mean, wouldn't that partner fermions with bosons in the same way?
So what happens then in those, so they would be called like, n=2 supersymmetry, n=4 supersymmetry. What happens then is you build up multiplets. So you can kind of think of them as consisting of like, well, it turns out 2 of these spin 0, spin 1/2 multiplets gets combined in with the spin 1/2, spin 1 multiplet. And that then sort of relates spin 0 and spin 1. And if you do it even more, you can maybe throw in a spin 3/2 particle. But I guess 2 things. One is those theories lead to so many connections, so many constraints between different things that they're not allowed. The very first implication is that you don't have chiral fermions. So obviously we have a lot of chiral fermions in the standard model. And so you have to do something a little bit more complicated to get chiral fermions. The second point is just that none of the motivations I've talked about or will talk about rely on that, right? So although that might be a beautiful thing theoretically, if you want to solve the gauge hierarchy problem, if you want to have a dark matter particle, you don't need to have any more sophisticated supersymmetric theory. All you need is the ingredients that we've got here. And so for phenomenology, by far, the most studied supersymmetric theories are simply the ones I'm talking about here, which are called n=1 supersymmetry.
I think you maybe hinted at this a little bit, but are the new particles in the Higgs sector potential dark matter candidates also?
Yes, good. So we'll see that in just a second. So that actually, yes, these Higgsinos over here are potential dark matter candidates. This one is the charged Higgsino. Obviously, that's not a good potential dark matter candidate because it's got electrical charge. But yeah, these other ones are, and yeah, I'll mention that. So that's exactly why I mentioned this sort of little caveat, which is that people always say supersymmetry is a doubling of the spectrum. It's not a doubling, it's a little bit more, and that little bit extra actually is important for dark matter.
And what about the particles on the standard model side? The new scalar, the Higgs sector particles.
So yeah, so basically, so you're very nicely giving me a good segue to my next slides. But basically, you can then start looking over here for all the potential dark matter candidates, and in particular, all the ones that are electrically neutral. And so, yeah, so for example, the neutrino has a scalar neutrino, a sneutrino, which is electrically neutral because the neutrino is electrically neutral. And you could think that that would be a dark matter candidate. So yeah, there's a bunch over here that we would want to look into.
Yeah, go ahead.
Yeah, short question. So the air parity you just discussed, and that makes particles stable, is the same as the discrete symmetry you discussed before for the discrete swing miracle, or they can be different in general?
Good. So yeah, the R parity that I discussed, where is it? Here is basically a realization of the general discrete parity discussion I had before. So it is the discrete parity. It is a Z2 symmetry. And it is exactly the discrete parity I talked about before. What I talked about before was this very general class, which is applicable to all models. In supersymmetry, that realization, that is the RP, the R parity, but that is the discrete parity I mentioned previously. Yeah.
Any more questions? Yeah.
Can the SUSY neutrinos help to give the normal neutrinos mass?
Interesting question. So the question was, can the SUSY neutrinos, the scalar neutrino or neutrino, can they help to give the neutrinos mass? Not really. We're going to see that supersymmetry has some very strong connections to neutrino mass, but typically they're through the line of thinking called grand unification. So I'll mention that. Let me think. These neutrinos, they probably, there's probably some theory out there where the small differences in neutrino mass are generated by a loops that includes neutrinos. So there's something like that. But probably the first thing you'd want to say when you think about supersymmetry and neutrino mass goes through grand unification. So let me talk about that, and then we can come back to this later if you want.
So to give neutrinos mass, because I really want them to have mass, I need to, and somehow the SUSY neutrinos can't give mass for deep reasons. I still need my somehow the sterals or something in a seesaw to give my normal neutrinos mass.
I couldn't quite hear exactly, but you said something about like, could there be a seesaw mechanism in supersymmetry to give neutrinos mass? And the answer is absolutely, yeah. So many of the standard mechanisms for giving neutrino mass are realizable in supersymmetry. And if anything, are more beautifully implemented in supersymmetry. Because as I'll mention, the idea that there's a sterile neutrino actually comes up in supersymmetry in a very, very beautiful way. So yeah, we'll come back to it. Is that okay?
In case I get mistaken. So in the seesaw, you need some right-handed guy, and this right-handed guy somehow is not your SUSY neutrinos, but some random guy in SUSY.
Yeah, that's right. So a sterile neutrino is a fermion, right? And so the super partners of the neutrinos, if we go back, so here's the neutrinos. The supersymmetry introduces neutrinos, but those are scalars. And so they're not extra neutrinos in this traditional sense. They're not fermions. And so they're not the sterile neutrino. That has to come from something outside of the framework I just mentioned here. Yeah, but that's an essential point. This neutrino here is a spin zero scalar.
I don't see any.
Okay, well, let me go on then. Okay, so here, as we left off, I just basically completed the story for you. add in a bunch of new weak scale particles. They do something nice with the gauge hierarchy problem. They screw up experimental observables, in this case, proton decay. We put in a discrete symmetry that fixes these problems. And now up pops the fact that the lightest supersymmetric particle is stable. And now we start running down the road of cosmology to figure out what is the dark matter candidate. So the dark matter candidate is the lightest supersymmetric particle, okay? Now, what is the lightest supersymmetric particle then? Okay, so this is in some sense an aside slide, but I think it's a fun slide because it's this sort of adhering to Weinberg's advice, go toward the messes. Okay, this is something that I think is underappreciated, and maybe there's something more to say here that's interesting. So what is the LSP? What is the dark matter candidate? Well, the first thing you say is it should be neutral. Like dark matter's got to be neutral. Well, okay, yes, but why exactly is that? And the story is much more interesting than I think is commonly appreciated. Because you could say, well, let's say I have a colored LSP, or charged, but let's say colored, like a gluido. Sure, that is a colored thing, but that's not going to just sit there as a colored thing. It will eventually bind with quarks. So at the end of the day, I will have a color neutral state. Similarly, if I have a charged, electrically charged dark matter particle, it will, get some electrons and make a neutral atom. So it's not at all clear that just because you say dark matter has to be neutral, that the fundamental constituents, the particles, have to be neutral, right? So it's not as like an open and shut case. We have to think about this a little bit more. Well, people, of course, have thought about this. The point, though, is that if you say you have a gluino, which has got an up and a down quark glommed onto it, and so now it's a color neutral kind of nugget, there are severe bounds because that gluino is a 500 GeV or 2 TeV. And so now you have a nucleus that is much heavier than any known nucleus, atomic nucleus. And so people have gone on to look for these things. Okay, they've looked for by basically doing these incredible experiments in seawater. So you take a liter of seawater and you basically go searching through that to find if there's anomalously heavy nuclei. And they don't find it. And then they do something really clever, which is they go down about, I don't know, thousands of meters to deep seawater, because actually, if there were these heavy nuggets, they would preferentially settle to the bottom of the ocean. So if you can look down there, you can get much stronger sensitivity. So they go down thousands of meters, get a liter of water from down there, bring it back up to the surface and sift through it and look for atomic, crazy exotic nuclei. And again, they don't see it. So, okay, so that then would seem to eliminate this possibility. Sure, the colored thing binds with uncolored stuff to make it color neutral, but you know that there's no heavy color neutral nuggets. And here are some of the bounds on this. Okay, this is from this great, completely underappreciated paper by Kudo and Yamaguchi, 2001. This is the mass of the dark matter particle, or the exotic nucleus. And this is the bound on its density relative to the density of hydrogen on Earth. And all these lines are upper limits, and all these dots are upper limits. And so by sifting through seawater, you know that there can't be very much of this at the level of like 10 to the minus 20 or 10 to the minus 28 of the abundance of hydrogen on Earth. Okay, so you might say, okay, there, we consider that, but well, no, that doesn't work. But then someone can come back and say, well, but what about inflation? We keep hearing about this inflation. Inflation dilutes away all these.
We're running a little bit late, just that you know.
So, oh my gosh, I misjudged the time completely. Okay, so, wow, okay. So let me, I'll talk to you, Yuri, after this. Let me finish this slide and then maybe I can wrap up, okay? Okay, so let me just say that inflation can dilute this away, but then of course we do have to reheat the universe. And so you can ask, if you reheat the universe to 1 MeV, do you make many of these new particles? And to cut this beautiful story short, the point is that they showed that if the masses are less than a TeV, in the reheating of the universe to 1 MeV, you will violate these bounds. You will generate too many of these charged or colored dark matter particles. However, if the dark matter particles are charged or colored but are heavier than a TeV, actually you could be fine. So as far as I know, this is a caveat to this. You might think dark matter has to be neutral. It's not necessarily true. I will assume it's neutral from here on out, but there is something here, and it may be the case that you could perfectly well have a stable gluino that's 2 TeV in mass, which doesn't violate any bounds. Okay, so what I was going to do next is I was going to then go through and look for all the neutral SUSY particles and figure out which of these could be good dark matter candidates. But since I've run long, I will stop here. I might want to propose that, given all the good questions here, we can consider that part of the Thursday discussion, and so that I can actually lecture into Thursday. But let me talk with the organizers about that to see how we can deal with the fact that I've gone a little too slow here. But let me stop now.
Okay, yeah, we can talk about it.
Okay, Yuri. Yuri, hi. Do you want to talk now, Yuri, or do you want?
So the idea is to introduce each other through short talks. So the idea is that the first 19 names in the alphabet go on the first Monday and the second 19 the second Monday. So we have a list of participants somewhere. Probably we'll have to circulate.
Yeah, we should send the whole list so that you know. If you're on A, your name.